All right, good morning to everyone. So today we will look at group 16 or group 6A and on the element sulfur. Okay. All right, introduction. So a sulfur exists as a free element, right? Also known as brimstone, which are formed by bacterial action on volcanic gas, the hydrogen sulfide. Okay. And this is the one that gives us the foul smelling or pungent smell of the sulfur. Okay, so actually the pure sulfur has no it is odorless, but this is the one. All right, when we are close to volcanic areas, active volcanic active areas will smell this is the hydrogen sulfide. Okay, so there are ores or bahan mentah, which is pyrite. Okay, and pyrite is also known as the fool's gold because it looks like gold. All right, but it's not gold. Okay, you have also other ores. Okay, iron sulfide, galena, lead sulfide, sphalerite, zinc sulfide. And sulfur exists as an S8 molecule, right, in the form of a pocket ring in a crown shape. So this is the shape. Okay, and it can also form different orientations. Okay, although it has this S8 molecule in a ring shape, but these ring shapes can also arrange in different orientation in the crystal structure to form the alpha, beta, and the lambda, and as well as the others. There are more than that. Okay, but the stable one is the alpha sulfur, which is in rhombic. Okay, rhombic structure. Okay, so let's look at the allotropes of sulfur. The two forms of S8 rings, okay, they arrange differently, right? So here is this is the stable structure, which is the rhombic, right? So rhombic is thermodynamically stable. It is in a granulated form. Here at the room temperatures will be in alpha rhombic shape. When the temperature increases above 97 degrees, it will form the beta monoclinic sulfur, right? This is the one. And it has a needle-like shape, okay? Needle-like form. And this is a metastable actually, and it can actually convert to the lambda sulfur, which is in liquid form. So the first two is actually in solid state, okay? The lambda is in a liquid state. And above 119 degrees, it will form the lambda sulfur. So in your experiment 5, for group 16, you'll be looking at sulfur, experiment on sulfur. And I believe during the experiment, you will have a lot of this pungent smell throughout. You can smell throughout in the lab, right, due to the hydrogen sulfide. So you also do one of the experiment. I think one of the first few experiments where you will heat up the solid sulfur, okay, and after that you will cool it down, filter it, and most probably you get this crystal-like shapes. So you know that you're actually forming the monoclinic sulfur. Okay. So write down all the observations, whether they are in liquid form or whether they are in solid form after heating up and things like that. All right. So you can try to explain the observations, okay, based on the knowledge that you have from what you have learned in the lecture. All right, now we will look at the extraction of sulfur. So this process is introduced by a German scientist. Okay, his name is Frasch, and it's known as the Frasch process. And the principle behind this process is due to its the low melting point and low density of sulfur. Okay, it operates based on this principle. So the superheated water, right, at the temperature of 165 degrees and at high pressure is pumped down the outermost of the 3 concentric pipes. So here we have pipes. Okay, if we look here, this is the outermost. all right, outermost pipe, and here in the center you have another channel here in the center. So superheated water is channeled through the outermost pipe. So can someone tell me, all right, so why do we need high pressure for the superheated water? Okay, can you explain to me? So you can actually comment at the comment section below and explain why high pressure is needed for the superheated water. Okay, so it is heated at 165 degrees. So what happens when the water is heated at 165 degrees? All right, so it's related to why we need a higher pressure. Now, then the compressed air is pumped down the innermost pipe, and we have a compressed air that is pumped down the center pipe. Okay, so the superheated water will mix with the sulfur, all right, the molten sulfur, and it will melt the sulfur and forms a liquid sulfur. And when the liquid sulfur is mixed with the compressed air, it will form an emulsion. Okay, and this emulsion is less dense than water, so it will rise. Okay, so it has a low density, so it will rise and come out as a the liquid sulfur. Okay, so sulfur obtained through this process has about 99.5% purity. Okay, so it's quite efficient using this process. Right? Okay, so next, let's look at the properties. So it's odorless, tasteless, light yellow, non-metallic sulfur. Right? So pure sulfur is odorless. Okay, it has no smell. Right? Sulfur is not readily wetted or dissolved by water. Okay, so rhombic and monoclinic sulfur are soluble to a limited extent in most organic solvents. Okay, and the organic solvents that is normally used is the carbon sulfide, okay, disulfide, which is commonly used, okay, to dissolve sulfur. It is a reactive element, combines with all other elements except inert gases, gold and platinum. Okay, a high degree of solubility is attained in carbon disulfide, which I have mentioned, which is often used to dissolve the rhombic sulfur for analysis. Sulfur is flammable and it burns in the air with blue flame. So remember the observations. Okay, it's very important. Okay, next we'll look at some of the chemical properties. So it reacts with oxygen through combustion process, and will form the sulfur dioxide gas. And the sulfur dioxide, if we continue with the oxidation, it will form the sulfur trioxide. So in such a process, in the second process, normally a catalyst is needed because this process proceeds quite slowly. So a catalyst is needed. Okay, heating with metal, it becomes metal sulfide. Okay, so these are the common ones, metal sulfide. And when it reacts with concentrated acid, okay, it can also form the sulfur react with concentrated acid. It can also form sulfur dioxide. Okay. Uses. All right, most of the sulfur is used to produce sulfuric acid. Okay, so this is a very important compound, the sulfuric acid. So one of the uses is in your car battery. Okay, the wet car battery. So the car battery is actually very corrosive. So you have to be very careful. Okay, so you can look at how the process. What is the process involved in the car battery? All right, why sulfuric acid is needed? Okay, please look it up. Okay, next, sulfur is a component of black gunpowder. It's a mixture of potassium nitrate, carbon, and sulfur, and a mixture of sulfur. All right. It is used in the vulcanization of natural rubber as a fungicide and as a fumigant. So it can be used. It is very important in Malaysia. We know that we have natural rubber, and how do we improve the mechanical properties of the rubber? We can actually do the vulcanization, okay, of natural rubber as a fungicide and as a fumigant. So we can also eliminate pests, right? For example, termites, okay, from buildings. We can also use sulfur, okay, to fumigate and chase away the termites. Sulfur compounds are used in the bleaching of dry fruits and for paper products. So it can also use in bleaching of dry fruits, and many of the fruits actually, especially used for when the fruits are being transported to other countries, for instance. So it has to be kept, uh, it has to be bleached, it has to be kept properly so that uh, it can be safe and it would not get spoiled. Okay, when it reaches its destination. Right? So you can please find out, okay, how does it work? How does the bleaching of dry fruit works? All right, and for paper products as well. Next, we will look at compounds of sulfur. So we have the metallic sulfide, which is ionic. Okay, so all metallic sulfides are solid and dark or black in color, except for zinc sulfide and lead sulfide. They are yellow solids. And ionic sulfide from highly electropositive metals undergo hydrolysis, resulting in a basic solution. Okay, so it's ionic. All right, so it when it reacts, it can undergo the when it reacts with water. All right, this is the anionic sulfide. When it reacts with water, it will form the hydroxyl groups. Okay, which is a basic solution. They are mostly insoluble in water. Okay, but those that have interacts with the highly electropositive metals, okay, they are able to dissolve in water. Okay, but most of them are insoluble in water. React with acids to form uh, hydrogen sulfide. Okay, dihydrogen sulfide. So this is one of the experiments. Okay, I think most probably you also do in your experiment. So for your experiment 5, I believe you will have, I mean, the whole lab, okay, will smell of very pungent sulfur dihydrogen sulfide. Okay, so it'll be very smelly. I believe so during the experiment. Okay. Right, next, let's look at the example, which is the hydrogen sulfide. Here we see it is a covalent sulfide, right? It has a colorless gas, foul smelling like rotten egg smell. Okay, very similar to rotten egg smell. Extremely toxic, it's a toxic gas, dissolved in water, okay, and it forms an acidic solution. So, and you can actually find this hydrogen sulfide at the volcanic active areas, and so it's very dangerous. You have to wear masks and goggles, things like that, because when it goes into your respiratory system, it can actually dissolve and it will form an acidic solution. So it is actually relatively corrosive. Okay, it can burn your eyes, burn your respiratory tract. Easily oxidized, it can oxidize with oxygen to form the sulfur dioxide. Okay, as a reducing agent, so it can reduce. This is your permanganate, all right, with the oxidation of positive 7, okay, for the manganese, and the manganese will then be reduced, okay, to positive 4, right. Carbon disulfide is a colorless liquid with fouling smell, solvent for sulfur, phosphorus, iodine, rubber, and wax. So it's very useful, the carbon disulfide. Okay. But however, it's relatively unstable. It hydrolyzes in water, okay, to form the hydrogen sulfide, okay, and carbon dioxide. Right. Next, we will look at the oxides. So there are two oxides here. One oxide has the oxidation state for the sulfur positive 4. All right. The other one is with positive 6, okay, which is the sulfur trioxide. The sulfur dioxide has the oxidation number of 4 for the sulfur. So these are the structures. So please know how to draw them. Okay. Hybridizations, they are the same. Okay. And on the left, the sulfur dioxide, the one of the hybridized orbital involve the lone pair of electrons. Okay. The geometry is a band shape on your left, and on the right, it's a trigonal planar shape. And here, I believe you have known the notation, okay, for the type of molecule. And here is the electron configuration, arrangement of electrons. So the sp2 here, it involves one of the paired electrons being hybridized. And on the right, for the sulfur trioxide, all of them are unpaired. Okay, so they're able to receive
they are able to share electrons, okay, and pair them with the oxygen atoms. Okay, so sulfur dioxide, it is colorless gas, a choking smell, and it's poisonous gas. Sulfur trioxide is a colorless gas as well, dissolved in water to form the sulfuric acid. So this is a important process for the formation of sulfuric acid. Reaction with sulfuric acid, okay, to form oleum. So oleum is a compound that is normally transported, okay. So it forms oleum and not a pure sulfuric acid, okay, for transportation. So we know that sulfuric acid, a pure sulfuric acid with high concentration, can be very dangerous, very disastrous. So if there's any accident happens during transportation, it can cause a lot of damage because it's very corrosive. And so it's much safer actually to have this reaction to form the oleum. Okay, and I think most of the time in the lab as well, you also find this oleum. All right, so whenever we want, we can actually, whenever we want the sulfuric acid, what we can do is we mix it with water. Okay, we can actually form the sulfuric acid. Okay, right. Next is the sulfur dioxide. The chemical properties of sulfur dioxide, it reacts with water to form acid solution. So it also formed acid solution, okay, which is the acid rain phenomenon. Okay, this is the sulfurous acid, and it reacts with alkali as well, forming sulfide salts. Okay, it can react with a base to form the sulfide salt. Okay, it is a reducing agent. It can reduce. Here is some example. Okay, we can reduce this. If you see here the permanganate again, all right, it can reduce it from positive, is a positive 4, right, to positive 2. Okay, so it will tend to oxidize itself. Okay, at the same time, it will reduce other species. Here as well, your permanganate to chromium. Okay, it will also it can also act as a oxidizing agent. All right, and itself is being reduced. Okay, so it also depends on the reactivity of the metals. Okay. Next, we have sources of sulfur dioxide. So it is an air pollutant, volcano activities, the emission of sulfur dioxide from the high temperature of molten earth through the combustion of sulfide ores, coal, and oil. Okay, you can also form the sulfur dioxide. Roasting of anhydride calcium sulfate with coke. Okay, it can also form the sulfur dioxide. All right. Reaction of sulfide salts with acid. Okay, it can also form sulfur dioxide, and a reaction with metal with concentrated sulfuric acid. Okay, so these are some of the sources of air pollution. Okay, then we have the sulfur trioxide. Okay, this is an important one. It is prepared through the process which is known as the contact process. Okay, commercially, this is the process that is being used to produce sulfur trioxide. Okay, so you have sulfur dioxide, you oxidize it to form sulfur trioxide, or heating of ferrum, okay, iron sulfate, okay, to form the sulfur trioxide. You can also dehydrate concentrated sulfuric acid, okay, by solid P2O5, okay, the phosphorus oxide, which we have learned in our previous chapter. So it is the basic unit, okay. We see in the chapter we have this, or the P4O10, okay, which is the dimerized species. So this is the basic unit, and this is the one that is saturated, okay, the one that is saturated with oxygen. If we have an excess of oxygen, it will and it reacts with the white phosphorus, it can actually form the basic unit P2O5 or the P4O10. Okay. All right. So this is sulfuric acid. It can form the sulfur trioxide. Okay. All right. The properties forming the crystals when it's cooled. at negative 83 degrees Celsius. So it has three forms. Okay, you have the alpha sulfur trioxide, which is a cyclic trimetric form. This is the one. This is the structure. Okay, please know how to draw them. You also have the beta form, which is a cube transparent crystal cross-link of SO4 sulfate into layers, which is metastable actually. So it will cross between these two structures. And the other one is the gamma sulfur trioxide, a needle-like crystal with infinite helical chains. So helical, it is just like the DNA, all right, a helical shape. With tetrahedral structure. So the SO4 has a tetrahedral structure. This is a tetrahedral structure. Okay, and it's most stable at sulfur trioxide solid. Okay, so this is the one in a polymeric chain. Okay, reaction with water. It reacts with water to form the sulfuric acid. Reaction with sulfuric acid produces oleum. So we have seen this in our previous slide. Okay. Okay, then we will look at the halides of sulfur. So sulfur halides exist for fluorine and chlorine. Okay, for bromine as well. Okay, but iodine does not exist. So as you go down the group, so what happens as you go down the group in the halide and the halogen group? So what happens is that the size of the atomic size grows bigger, okay, and larger. So the ionic size as well, it grows larger. All right. So we know that it's able to form, all right, it's able to form the sulfur halides very quickly, especially iodine, but it's also easily broken. Okay, it's easily broken. So because of the size and the lower electronegativity of the iodine, so it can form very quickly, but it can also break very easily. So it in the normal conditions, you don't actually see this. Okay, the sulfur iodides. Okay, so we also have the disulfur dihalides. Okay, once again, it exists for the fluorine, chlorine, and bromine. You can do the direct halogenation. Okay, sulfur with the halogen. So disulfur difluoride is in gas form. As you go down the group, the disulfur dichloride is a yellow liquid. And as you go down, the disulfur dibromide is an unstable liquid structure. So you can see that it decreases in stability, okay, due to the weak bond that is formed. So this is the structure. It has a sp3 hybridized structure. Okay, it hydrolyzes in water. It hydrolyzes the water to form sulfuric acid and forms the sulfur. This is the indication of a precipitate. Okay. The disulfur dichloride reacts further with chlorine to produce sulfur dichloride. Okay, it can form this reaction. And the sulfur dichloride reacts with ethane, okay, which gives the mustard gas. This is the mustard gas. This is the structure of the mustard gas, and it's used in warfare. So it can actually cause blister on the skin. Okay, it's very corrosive and it's used in warfare. All right. Next, we have the sulfur tetrahalide. It forms a distorted trigonal bipyramid. Okay, here you can see it is trigonal. It's a trigonal bipyramid, which includes the lone pair of electrons. Okay, but it's a distorted one, as we know that if you look at the Vesper theory, the lone pair of electrons will have a stronger you have the stronger repulsion, okay, with the bonded electrons, okay, as compared to the bonded electrons and as compared to the between the bonded electrons and the bonded electrons. So it will push away all the other bonded electrons far away, okay, to form a distorted trigonal bipyramid. So the preparation here again, it can react directly, direct halogenation to form the sulfur tetrahalide. okay, for chlorine. But for the fluorine, since it's very reactive, so the sulfur tetrafluoride has to be at very low temperature and in inert atmosphere, okay, because it's too reactive, it can explode, okay, so it's very dangerous. So reaction, hydrolysis in water and alkali, okay, so it can hydrolyze and goes back to the sulfur dioxide, okay. If you have a base, it will form the sulfur trioxide ion, and it's able to expand the octet. So remember, it has a d orbital. Sulfur has a d orbital, and it can accept more of the halide. Since halide has a lot of electron, lone pair of electrons, it can accept the donation from the halides. Okay. All right. So next we have the sulfur hexahalides. The synthesis, sulfur reacts directly with all halogen except iodine to form the sulfur hexahalide. Okay. So this is the hybridization. You have the sp3d2 hybridization. So you also learn other types of hybridization, which is the D2 sp3. Okay, when you go into the coordination chemistry subject, you see this a lot in the valence bond theory for coordination compounds. Okay, properties: colorless, odorless, tasteless, non-toxic, thermally stable, and insoluble in water. So it's very stable. So not a Lewis base. Okay, no available non-bonding lone pair of electrons. So it has been pulled away. So most of the electrons in the sulfur has been pulled away from the has been pulled towards the fluorine. Okay, so it cannot act as a Lewis base, the sulfur. So despite the positive 6 oxidation number, it is not an oxidizing agent because the fluorine atoms protect the sulfur. So since we have a three-dimensional arrangement of the fluorine around the sulfur, so it acts as a protection. Okay, so no other species can actually attack the the sulfur, which is located at the center. Okay, it's a much better electrical insulator than air, right? Okay, so finally we'll look into the oxo acids. So we have this is the sulfurous acid, all right, or sulfuric 4 with the oxidation number of 4 acid. So it is derived from sulfur dioxide. Okay, so please remember the equation is from sulfur dioxide. As for the phosphorus acid with the oxidation number of 6, it derives from sulfur trioxide. So these are the differences. Here is the sulfide ion, anion. All right, this is the structure. When it deprotonates, it can deprotonate 2 of the hydrogen and form 2 protons. Okay, and this is the structure. Right. Next, we have the properties, ionization. So it can ionize, as we've seen earlier in the previous slide. It is a dibasic acid since it can deprotonate 2 of its hydrogen. Okay, and we see the Ka value for the first deprotonation, the ionization, it forms a higher Ka value, a higher ionization constant, acid ionization constant. So it's much stronger as compared to the second deprotonation. The sulfide salt is obtained by reacting the acid with alkali. So it's like an acid and base reaction, okay, and it forms a salt. The salt, when dissolves in water, undergoes hydrolysis. So it's relatively, it is much less acidic as compared to the sulfuric acid, which has the oxidation number of 6 for the sulfur. Okay, here you see that when the species, all right, the salt that is produced, it will undergo hydrolysis with water to form a basic solution. Okay, right. Okay, next, finally, we have the sulfuric acid. So the sulfuric acid has the oxidation number of 6. It's derived from sulfur trioxide. Okay, so we heat it up with water to form the sulfuric acid. So we have some other side products. Okay, some other side species. So this reaction should be continued. Okay, continuously in hot water to form the final product, which is the sulfuric acid. Okay, again here. This is the sulfate anion. all right? It also deprotonates two of the hydrogen of the hydroxyl groups, okay, to form the sulfate and ion. The industrial manufacture of sulfuric acid, I think we have looked into this previously in the previous slides. So let's just go through it. It's called the contact process. The process involves several steps. So combustion. So from sulfur, pure sulfur, we combust it and with oxygen to form the sulfur dioxide. And the oxidation continues. The sulfur dioxide will then form the sulfur trioxide. And sulfur trioxide will be transformed to sulfuric acid through the dissolution of sulfur trioxide into concentrated sulfuric acid, forming oleum. All right. So it can actually also dissolve directly to water, but it will cause fog to form. Okay, carbos to form, and so it's very difficult to contain. Okay, so most of the time they will actually just react with sulfuric acid to form this oleum, right? So an oleum, in the addition of certain amount of water to oleum, you can actually obtain the acid, which is known as the sulfuric acid. Okay. Properties: it is a diabasic acid. It's a strong acid. Okay. So the concentrated sulfuric acid is viscous. It's a viscous liquid. So what is viscous? What does viscous mean? Okay, so this can be a question. So please comment at the section below. What does it mean by viscous? Okay, due to the hydrogen bond between the molecules. So it will form somewhat like a polymeric chain with high boiling point due to the hydrogen bond between the molecules. Okay. So the concentrated acid, sulfuric acid, it can act as a dehydrating agent. So a dehydrating agent, for this, I think it's very common in organic chemistry. You will see that it can actually, if you see here this equation, all right, we can actually form the ethene, right? The double bond. So it will remove one of the hydroxyl group and a hydrogen and remove a water molecule, right? So it's very important in the organic chemistry. And for this, I want you to view a video, all right? I've posted in a forum. So kindly follow the instructions, okay, which I will show you in the next slide. Okay, you have to comment, all right, to show that you have actually watched this video. Okay. In dilute concentration acts as an acid. Okay, and most of the time we dilute them in the lab, all right, because if it's too concentrated, it will dehydrate your reaction. So the purpose is to just act as an acid, okay, for neutralization. So normally we will dilute them. In concentrated and hot as oxidizing agent, so it can oxidize almost most of the compounds actually. Okay, so it's a very good acid, and it is actually very important acids in the steel industry, for example, and many of the industry that deals with metal or semiconductor, because acids can actually age the metal, okay, in a certain way. Maybe it's very useful in the semiconductor industry. Okay, so you can read up on it. Okay. So this is the activity which I want you to go and have a look at this. So please comment please comment the experiment. Sorry, this is a spelling mistake here. Comment the experiment. So each student must post a minimum of one discussion or reply to any post. So you can help your friends as well. Whatever post that you see, you can also help them. And this forum will be open until tonight, okay, midnight, okay, 12 a.m. So please help your other friends during the discussion. You can post and you can post your questions. So here are some of the questions that you can reply to. So what is the overall equation for the reaction? What are your observations? Predict what are the physical or chemical properties, and what are the usage of the product that was formed. So you can suggest what can we use that final product for, or any other comments or suggestions. So I want you guys to chat with each other. All right. Anything that you observe based on your observation. Okay. And also based on these questions that we have.
Okay, so sulfuric acid is also used as a sulfonation agent, especially in the organic synthesis. All right, to form the substituent group with the aromatic ring. Okay. It's also used as a catalyst in esterification. I think this is most of you are very familiar with this. So one of the starting materials is an acid, and the other one is an alcohol. And with the sulfuric acid as a dehydration agent, so it will remove a water molecule. Okay. And form the ester. Okay, uses. It is also used as a fertilizer. So earlier we have seen the ammonium nitrate, right, which is the fertilizer, and this is also a fertilizer. It can be used as a fertilizer. So what are the differences? Can you tell me what are the differences? Which is better, using ammonium sulfate or using ammonium nitrate? Which is more suitable, or which is better? Can you suggest? Or is there any differences? Or is there any pros and cons using ammonium nitrate as well in comparison with ammonium sulfate? Or is there any advantages using either one of them? So please comment. All right, please comment in the comment section. So chemicals for detergent, ether, esters, dehydrating agent to remove water from gas, liquid, and solid. Also as a pigment, okay, TiO2, titanium dioxide, is a white pigment that we use in paint, for example, on the wall, paint on the wall. It uses the titanium dioxide, okay, to give an opaque opaque color, opaque white color to the paint. So it can also give you a different hue or different tone to the white color, white paint, using sulfate. All right. To produce concentrated hydrochloric acid, we can react it with the salt, okay, with sulfuric acid. Okay, we can actually form the hydrochloric acid. Okay, these are some of the general uses. You can see that about 62% is used in the fertilizer industry. Okay, and there are also some other is used as starting material. Okay, chemicals in the industry, right? Rubbers, batteries, explosives, pigment. All right, in polymer, textiles, rayons, films, petroleum refining. Okay, we know that petroleum has a lot of sulfur. Okay, so they have to remove them, refine them. Okay, iron, steel, some of these impurities, okay, is introduced into iron to form different mechanical strength of steel. Okay, so sulfur can be also one of the impurity. Okay. So that's all for our lesson today. So please remember to to comment in the comment section below. You can ask any questions, and also you can reply to those questions that I've asked you in the lecture video, as well as participate in the forum. All right, I've already posted a forum. View the video, all right, which is on the dehydrating properties of sulfuric acid. Okay, comment based on your observation. What do you see? What are the properties of the products form? What are the equations? Okay, you can also comment on the equation involved for the reaction.